Advanced Placement Chemistry. This is lesson 3, and it's on the subject of measurements. So what we're going to talk about today are two things. A math concept called significant figures. And this tells you how many digits you should write down. So when you do a calculation on your calculator, sometimes it might display 9 digits to your answer when you divide two numbers, for example. But you don't write down every one of those digits. So significant figures deals with the rules of how many digits do you write down for an answer. Related to that is measurements. Measurements tells you how many digits you should write a measurement to. So when you're in the lab, you write down your measurement, whether you're weighing a mass or whether you're looking at a volume in a cylinder. It tells you how many digits you should make that measurement. So first you write down the proper number of digits when you do a measurement, and then you use the proper number of digits when you're doing calculations with that number to determine how many digits you should write for your answer. So you'll see how that works. We're going to deal with the significant figures first, and then we'll go to measurements. So first of all is the concept of rounding. I think most of you are familiar with. Rounding is a process of limiting the number of digits after a decimal. So example, round the following number to 3 significant figures. All of those are possible significant figures, and we're going to talk about that subject right now. Significant figures will be covered later, actually right now. So when you round that to 3, you only want those 3 digits to show. The other 3 you want to go away. So how do you determine what digits you should write down? If the next digit after the 3 that you're interested in is to the right of the 7, if that is less than 5, then the 7 stays as a 7. If that number is greater than 5, then the 7 rounds up to an 8. So you can see that it is greater than 5. The number 6 is greater than 5. And so that means you would round the 7 up to an 8, and so your answer there would be 3.47. So that's how rounding works. I think you have done that before. Significant figures indicate the precision of a measurement. So in the last lesson we talked about precision. And so what we're going to do is see how do you indicate that when you do a math calculation. So in math terms, they provide a set of rules for how many digits you should use in your answer based on the precision of your laboratory measurements. So let's take an example here. Let's say that's a room. That's the floor of a room, and you're measuring it. So you measure the width of the room with a laser device that's very precise to 1/10,000th of a meter. So that's the number 5.2143, very precise measurement. The length of the room you measure with an old meter stick, and it's less precise, and you just measure that to 8.1 meters. So to obtain the area, you know this from math, you multiply the length times the width. So that would be 8.1 times 5.2143, and that would give you an answer of 42.23583 square meters. So the value 42.23583 square meters indicates a level of precision for the measurement that is misleading, because the length of the measurement, or the length measurement, that's the 8.1, could have actually been anywhere between 8.05 and 8.14. So think about that. 8.1 could have been 8.05 rounded up, or it could have been 8.14 rounded down. So that actual measurement could have been anywhere between those two numbers. This means that the area could have ranged between 41.975 meters squared, if you did the math on that, or 42.444 meters squared. So you see there's quite a variability there of what that measurement could have actually been. The rules of significant figures limit the number of digits you can use in this answer to 2. So that means the answer would be not 42.23583, but just 42, because you could only have 2 significant figures. So what you're about to learn is how do you determine that? Why did we say it can only be 2 significant figures, and that our answer has to be expressed as simply 42 without all those numbers after the decimal? So here are the rules of significant figures. First of all non-zero digits are significant. So 1 through 9 are always considered to be significant. Zeros to the left of the leftmost non-zero digit are never significant. Zeros in between non-zero digits are always significant. Zeros to the right of the rightmost non-zero digits are significant if there is a decimal point and not significant if there's not a decimal point. So let's go ahead and see some examples, and that will make it a little clearer. So take this number. How many significant figures is that? Well, they're all non-zero, so all non-zero digits are significant. So all 3 of those digits would be significant figures. So that would be 3. How about this? 3045, 3045. That's 4 significant figures. A zero between non-zero digits is always significant. How about this? 6020. That's 3 significant figures. No decimals, so trailing 0 on the right is not significant or is uncertain. And I'll tell you how to deal with that situation, that maybe whoever wrote that number meant it to be significant, or maybe they didn't mean it to be significant. You can't be sure, really. But for our class, we're gonna follow the rules strictly. So if there's no decimal, we are going to say that that is not a significant 0. Here are some more examples. Okay, now what about this? How many significant figures? Think about it. You can always pause the video, remember, and think about this. Okay, that's going to be 5 significant figures, leading zeros. That means zeros before you get to your first non-zero digit, which would be that 2. Leading zeros are never significant. What about this? 1 significant figure. Trailing zeros are not significant or are uncertain if no decimal point. What about this number? That's 8 significant figures. All zeros are significant. Because there's a decimal point, that last 0, the one furthest on the right, is a significant figure. How about this? 4 significant figures. Leading zeros to the left of the 1 are not significant. Trailing zeros right of the 1 are significant because there's a decimal point there. Multiplication. The numbers being multiplied are called multiplicands, and the answer is called the product. Rules for multiplication. The product should contain the same number of significant figures as the multiplicand with the least number of significant figures. So let's see some examples. 2 times 4. So the 2 numbers you're multiplying each have 1 significant figure. That means your answer on the calculator would be that, 8. But your significant figure answer would also be 8. Because you show your answer to 1 significant figure. So 2 and 4 have 1 significant figure, so the answer has 1 sig fig. Sometimes we just say it that way because it's a lot shorter. 31 times 23, now your calculator would tell you the answer to that is 713. What should the significant figure answer be? It should be 710 without a decimal point. Each of the multiplicands, 31 and 23, has 2 significant figures, so the answer is limited to 2 significant figures. The last digit, 3, should be rounded down to a 0. Okay, so you can't just eliminate the 3 or the 0, otherwise you'd have the number 71. That's not even close to what the answer should be. You just basically have to turn it into a 0 that's not significant because there's no decimal point there. Okay, how about this? So what you're seeing there is the calculator answer for multiplying these 2 numbers, 0.3432. So the significant figure answer would be 0.34. It can only have 2 significant figures because 3.3 has only 2 significant figures. So 0.104 has 3 significant figures and 3.3 has 2 significant figures, so the answer is limited to 2 significant figures. The answer is rounded down to 0.34. How about this? What you're seeing, 64.056, is what your calculator would show. That should be rounded to 64.1. Each of the multiplicands has 3 significant figures. So the answer is limited to 3 significant figures. The 5 rounds the 0 up to a 1. So that 0 in the calculator answer there will go up to a 1 and become 64.1. What about this? Now this one will make you a little crazy. 8,547 times 5 gives you 42,735. So what's that going to be? Okay, so it's going to be 40,000. The 5, which only has 1 significant figure, limits the answer to 1 significant figure. So it's going to be the furthest digit to the left. The 2 is rounded down to 0, and all remaining digits are zeros. Okay? So you're not going to just eliminate those digits after the 4. You have to turn them into zeros. In other words, you have 8,547, but you're multiplying it by a number 5. That 5 might be 4.5 rounded up to 5 or 5.49 rounded down to 5. It could be any number in between those. You just don't know. So you can't show 42,735 as your answer. You don't have that level of precision because the 5 limits the precision to which you can express your answer. So you just basically have to say it's about 40,000. It's somewhere around 40,000. Maybe a little less, maybe a little more. Okay, so let's do some more here. What's this going to be? There's your calculator answer. Okay, that's going to be your sig fig answer, all right? The 0.10 in the multiplican, one of the numbers you're multiplying, limits it to 2 significant figures, so your answer can only have 2 significant figures. You can't have that 4. The 0.10 limits the answer to 2 sig fig. The 4 is rounded down to 0, and the 1 and trailing 0 are the only significant figures. How about these two? 42. The measurement example on the earlier slide, that's the one we did at the very beginning, the 8.1 limits the answer to 2 sig fig. The 2 after the decimal is rounded down. So that second 2, the one that's after the decimal, gets rounded down, and you just have 42. That's 2 significant figures. Division also uses the same rule. So 3.246 divided by 2.8, that's what your calculator would read. And you say, well, how many digits should I actually show? And sometimes your teacher might be me, will say just kind of, a couple places after the decimal's good. But now you're learning the proper rules for how many places after the decimal. So this would be 1.2. 2 digits in the denominator set the answer at 2 sig fig. So the 2.8 is 2 sig fig, so your answer can only be 2 sig fig. How about this one? Which of those numbers has the least number of sig fig? The 3,400 does, 3,400. So your calculator answer you have to limit to 2 significant figures. So 3,400 divided by 987, the sig fig answer is 3.4. 3,400 has no decimal and is 2 significant figures. 987 is 3 significant figures, so the answer has 2 significant figures. What about this one? So there you're seeing the calculator answer for this particular division problem. 200. 0.8 is 1 significant figure. So only the 2 in the final answer is significant. The 3 rounds the 2 down. So in other words, it stays at a 2. It doesn't go up to a 3. There's no decimal in the final answer, making the 00 not significant. So 200, you can't just say 2. That's not correct. It's 200. Just remember, the significant figure answer has to be reasonably close to the actual calculator answer. 2 would not be close to 234, not even close. So it's 200, but the 2 zeros are not significant. The rules for addition and subtraction are totally different than what you just saw for multiplication and division. And let me just say that almost every calculation you do in chemistry, 99% of them will be multiplication division. So if you understand the principles you just learned, that it's the you take the number you're multiplying or dividing with the least number of significant figures, and that's how many should be in your answer. That's all you have to remember. The rules for addition and subtraction are quite a bit different, so let's see what they are. Rule for addition, subtraction. Line up the decimals to add or subtract numbers. Okay, that's what you always do when you add or subtract decimal numbers. The sig figs are determined by the number with the least number of digits after the decimal place. Okay, so let's just go to some examples to see what that means. So you're going to add those two numbers. So let's just answer that question up above, or identify what number that would be. It would be the 23.45. That has the least number of digits after the decimal. It has a 4 and a 5. That's 2 digits. So what you do is you draw a line right down alongside of that last digit in the number that has the least number of digits after the decimal, 23.45. Now you add, and you get 29.186. The only significant figures are going to be the 2, the 9, the 1, and the 8. The 6 is not going to be significant, so you use it to round the 8. So the 6 rounds the 8 up to a 9. The final answer is 29.19. So again, for addition, subtraction, the rules are not at all the same as they are for multiplication and division. So let's do a combination problem. The rules for combination problems. Use PEMDAS, order of operations, and keep track of the significant figures. Do not round until the end of the problem. Practically truncating, that means cutting off, after about the 4th place after the decimal is all right. Why is that? Because we're never going to have an answer that's going to have 4 or 5 significant figures after the decimal. We simply don't do measurements in this class that are that precise. Then you assign the correct significant figures at the end of the problem. So here we have 3.24 times 1.021 plus 12.1. So you're going to do the multiplication first. That's the order of operations. You're going to identify what the least number of significant figures is. Then you're going to take that, but you're not going to round it at that point. You're not going to cut it down to that. Then you're going to go ahead and add the 12.1, determine the number of significant figures there, and then you're going to do your rounding down. So let's see how that works. So 3.24 times 1.021 equals 3.30804. That's your calculator answer, but that's limited to 3 significant figures because of the 3.24. So just kind of note that number right above 3.30804 is that it's going to be 3 sig fig. Now you add the 12.01, but to the entire 3.30804. Don't cut it down before this step. So 12.1 plus that number is going to give you 15.40804. Now you do your addition rules for significant figures. You draw a line down by the 12.1, and that's going to limit you to the 3 significant figures, the 15.4. And the 0 is simply going to keep the 4 as a 4. So both steps 1 and 2 limit the answer to 3 significant figures. So the final answer is 15.4. Again, stop, pause, think about this. Even write it down, just scribble it on a piece of scratch paper until you get comfortable with the procedure. Compute the following. Okay, so let's do that. So order of operations says you do the multiplication first. 3 times 0.415 gives you 1.351. However, that number has to be limited to 1 significant figure because of the number 3. But you don't round it yet. You leave it at 1.353. Then you add that to the 6.02. You draw the red line next to the 2 because that number has the least number of digits after the decimal. And you end up with that number 7.373, and that last 3 rounds the 7 back down to a 7. It stays at a 7. So the addition produces 3 significant figures, but the multiplication limits the answer to 1 significant figure. Okay, so you have to go with the one that has the least number of significant figures, and so the answer for that is simply going to be 7. All right, It's just a little bit of practice and this will make sense to you. Rules for logarithms: we will hardly ever apply significant figures to logarithms, and we'll hardly ever do it with addition and subtraction, what you just saw. It's mostly going to be multiplications and divisions. So count the number of sig fig and the number from which the log is being taken. That's called the argument. This is the number of digits that should be after the decimal in the log, called the mantissa. So that's all mumbo jumbo. So let's go ahead and see an example. Log of 12.43 gives you that number on your calculator. So since the number 12.43 has 4 significant figures, there will be 4 digits after the decimal place in the final answer. So you will round that second 4, the one that's furthest to the right. The 7 will round it up to a 5. So you need to have 4 digits after the decimal point, 0945, because the 12.43 has 4 significant figures. Okay? Don't worry about this one. We'll hardly ever use it, but that's just the rule. Now let's talk about measurements. Distance. The ruler shows metric units on top, centimeters, and Imperial English units on the bottom. In chemistry, we do all measurements in metric, so you always want to be sure you're on the correct side of the ruler, not the inches side. You want to be on the meters or centimeters side. The number units on the top are centimeters, so each of those numbers you see, 1, 2, 3, 4, 5, are centimeters. The small lines in between each centimeter are millimeters. So there's 100 centimeters in a meter. There's 1,000 millimeters in a meter. There are 100 centimeters and 1,000 millimeters in a meter. Okay, so let's take a look at this. There is a ruler, or it could be a meter stick, and it's showing those numbers that you see along there are the centimeters. That arrow is pointing exactly at 4. So the level of precision that we measure is 0.00. Why? If we're measuring in centimeters, it's 0.00. And why is that? Because you can clearly see there's a 4 there. But we also have millimeter markings, those tiny lines. And those represent 0.1 centimeters. So we can definitely see to 4 point something. In this case, it's 4.0. But if it were over a little to the right, it would be 4.1 or 4.2. Okay? So millimeters represent precision of 0.1 centimeter. In addition, and this is key, the measurer is allowed to estimate 1 more decimal place. This allows the measurement to be 2 places after the decimal. Okay, so let's say you're going to see some examples of that. But when you're measuring this, you can go 2 places after the decimal. So now we see one that's pointing. It's supposed to be pointing exactly at 6 plus 7 more millimeters. So that's 6.7. Now, if you think it's pointing exactly at that 7th line after the 6, exactly, then it would be 6.70. You're allowed to guess that last digit. So 10.025. So the measure is after the 10 centimeter line and is estimated to be halfway between the 2 millimeter and 3 millimeter line. So the estimate is 10.2. You definitely see it's past the second small line, and you think it's about halfway between the second and the third. You're just guessing. It's just an estimate. Then you would say that's a 5. Okay? If it was a little more, it might have been a 6 or 7. But you're estimating that. Now you say, well, that seems kind of funny, you can guess a digit. But you definitely know it's greater than 10.2, and you can definitely see it's not as great as 10.3, so you're actually making your measurement more accurate by guessing about how far in between those 2 lines it is. So you always have a guess, what I call a guess digit at the end, okay? It's just an estimate. How about this one? 12.38. So the measure is after 12 centimeters and just before the 4 millimeter line, the 4th line after the 12. You think it's just before that, so you're estimating that it's an 8. Maybe it's really a 7, maybe it's really a 9. Again, you're guessing at it, but you're doing the best you can with your eyes to determine how far is that in between the in between the 3rd and 4th small line, and you're saying it's close to the fourth one, so we're going to say it's an 8. Okay, now this is a piece of glassware called a burette, and you use it to do what are called titrations, where you drip, 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 drip a solution out. So we're going to learn how to read this. So liquids form what appears a disc on top. You see how it looks like there's a little plate or a bowl or a disc up there. The disc is called a meniscus, and you can see it there. You can see that it has a thickness to it. The height of the liquid is measured from the bottom of the meniscus. So right where that red arrow is pointing, that's what you measure from, not from the top. You measure from the bottom of the meniscus. The reason is, if you could really see inside that meniscus, it's air. That liquid, which is water, is kind of creeping up the sides of the burette there, and so that's really just empty space inside of that meniscus. So really what you're reading is the bottom of the meniscus. Each of the small lines is a milliliter, ml, which equals a cubic centimeter, cm to the third. Now you're going to be using this quite a bit, a triple beam balance. So the illustration below shows the beams on a triple beam balance. The center beam is in increments of 100 grams. Okay, so you can see that center beam, it goes 0, 100, 200, 300. Now you notice there's little notches there. When you use that, and we'll practice using that, you have to be sure that that weight there is in one of the notches, not in between them. The top beam is in increments of 10 grams, and the bottom is in increments of grams. So the very bottom one is going to be your highest level of precision. Each of those numbers is a gram. Each of the little lines in between the numbers, 0, 1, 2, 3, 4, 5, is 1/10 of a gram. The reading on the scale to the right would be, so let's read it. You have 500 grams. You start with the biggest number. Then up on the top beam, you have 30, so 530. Then down on the bottom beam, you see that it's past 6, but not all the way to 7. So it's going to be 536. Now, which little line is that pointing to? You can see the little pointer on the bottom beam. It looks like it's pointing to an 8. So that's the highest level of precision that the scale can give you, is one place after the decimal, 536.8. But remember, you get a guess digit. If you think it's a little bit after that 8, but not all the way to the 9, you can put another digit there. In this case, you're guessing that the 0 is the estimate digit, and the resolution of the image is not clear enough to tell where the point lies between 8 and 9. But let's say you think it's right on 8. If you think it's exactly 8, you don't just write 536.8. You have to write 536.80. You have to put that guess digit in. Even if you think it's a 0, then you just write it as a 0. Time is measured in the same units in any system. So time is the same all around the world. There's clock time, seconds, minutes, hours, and then there's calendar time, days, weeks, months, years. Generally in chemistry, we're dealing with seconds and minutes in this level of chemistry. You can also have a century down there too. So that's it. So it's going to take a little practice with this, and we mainly practice this in lab when we do labs, to read our measurements to the proper precision, and then to do our calculations to the proper number of significant figures. Okay? This is not automatic. Probably none of you have ever learned this before. It'll take a little practice, but again, it's just a little practice, okay? It's something that will come through to you. So just learn it as you can, and you'll be fine. All right, we'll see you on the next lesson.